Good evening, everybody, and welcome to another edition of the USB Brown Bag. We have a very special guest this evening, the illustrious, the amazing, the suave and debonair Tim Davis, who is going to be teaching us about NSX. Couple of housekeeping rules before we get this going. Please get in on the conversation. We are monitoring Twitter on @vBrownBag. If you hashtag vBrownBag and fire us a question from there, both I and Ariel will be fielding those questions. If you are in the audience, we will also be taking the live questions and presenting them to Mr. Tim to knock out of the park. Again, our guest this evening is Tim Davis. He is at ALDTD. My name is Chris Williams. I am at Misswire. And without further ado, I'm very excited to hand Mr. Davis the presenter roles. There you go, sir.
Perfect. All right, let's do screen 2.
Awesome. I can see your screen.
All right, you see my logical switching with NSX?
I do, yes.
Great. So last week we got the NSX Micro Ninja series started off with the 101, and we went over the component overview, just basically kind of seeing what components we have and how they interact. So this week we're going to move on, and we're going to do layer 2 and layer 3, or switching and routing, and we're going to kind of go over how NSX handles that. We're really not going to dive like super deep into how switching and routing itself works, just kind of how NSX handles that. So let's get started. We're going to do here for this first deck a VXLAN overview, NSX for vSphere VXLAN enhancements, system architecture, VXLAN replication, and then packet walk. I'm going to try to time this out where we do 30 minutes of switching and then 30 minutes of routing, but we'll see how that works out. So NSX logical switching. When you're looking at switching in the data center and kind of, seeing how you're going to architect something or how things are working, there can be challenges, whether you have like multi-tenant segmentation, VM mobility from site to site or anywhere within your data center that requires layer 2 adjacency, or even some issues when you start doing like really, really large layer 2 environments, when you have to start looking into STP, which is spanning tree, and how you can design that, because that does start throwing out switch ports for you. And you can also have, when you have really, really large STP, times where when you lose a path, it has to just completely lock up and recalculate. And at hyperscale, this can cause problems. Also, things like MAC tables and forward tables, you can start to hit those limits in really, really large environments. So NSX can kind of solve for some of these issues, and really it's not like some huge crazy issue that everybody should be jumping over the fence for, but they are design decisions that you have to make, and with VXLAN and layer 2 in NSX, we're kind of trying to make that a little easier. So our scalable multi-tenancy across data centers, due to the fact that we're distributing switching to all of the different hosts, we're kind of able to help spread out a little bit more than if you were to take a standard L2 network. Enabling L2 over L3. This is by far the biggest thing that NSX does in terms of switching and routing, and this is really why we use VXLAN. And it's an encapsulation protocol that allows us to have layer 2 adjacency no matter what the underlay looks like. So if you're going in a spine leaf architecture in your data center, and you're going from rack to rack with equal cost multipath routing, you can still have layer 2 adjacency between the two. If you're doing site to site, say a multi-site NSX enterprise environment, and you've got some kind of layer 3 routing between the two sites, our encapsulation allows you to have that layer 2 adjacency between those sites. I have actually walked into customers before where they've said, I don't like encapsulation, it never works, overlay networks are bad. And then you ask them how they were trying to solve the layer 2 problem, and they would say, well, I was going to use OTV from Cisco. Well, OTV is overlay transport virtualization. It's an encapsulation protocol. It's exactly what it is. It's a different protocol, but it's still just encapsulation. As we talked about last week, Cisco does use VXLAN specifically. They did help work on the standard, and they use a little bit different version called IVXLAN in ACI fabric in order to do encapsulations. So logical switches do span across all of your physical hosts. Now, it's not all of your physical hosts. When configuring NSX, you set up what's called a transport zone. And this is kind of just a boundary of how far do I want my logical networks to go. Now, this isn't something that you would use as a security boundary or anything like that, because they are absolutely not. But most of the time, in 99.9% of designs, we say that just go ahead and use one transport zone and put it wherever you want anything. We get the question a lot, why would I want to use multiple transport zones? The one time that I've seen it used was because the customer had a mixture of desktop workloads and server workloads in the same environment, which we all know is bad for reasons. So the fact that they were mixing those workloads, they wanted to keep all the networking completely separate as much as they could in a logical sense. So we had them take and have multiple transport zones. Again, it's not a security boundary, just how far your switches will reach. So if you have that transport zone across 3 clusters, whenever you create a logical switch in that transport zone, it will go to every single one of those hosts. So let's look at our VXLAN protocol. And I apologize because these decks that I have today are a little wordy. So I'll try not to directly read them, but that may be how some of this comes across. So IP overlay networking, we use IP UDP for this. And I did talk about last week how even though it is UDP, which is unacknowledged on the other side, if you encapsulate TCP with UDP, even though that UDP encapsulation frame was dropped, the TCP on the other side was not acknowledged, so it will resend. So 24-bit VXLAN network identifier. This is kind of the big thing with VXLAN versus VLAN, and VLAN does not have that many bits, so you can only have like 4,000 some odd VLANs. And with VXLAN, with the 24 bits, you can actually have up to, I believe it's 16 million with that specific number. With NSX today, you can only have 10,000. That's just the number we support. I believe at some point that's going to be going up. But really, you're going from 4,000 VLANs to 10,000 VXLANs available. So if you're starting to hit that number, maybe you need to reevaluate your design. So VXLAN can cross layer 3 network boundaries. That's obvious because that's the whole point of why we use it. We're using it to encapsulate that traffic and send it across, whether it be layer 2 or layer 3. That's how we're giving you the ability to have 2 VMs that exist in completely different locations, the ability to be quote-unquote plugged into the same switch, even though they have to go across, different carriers and over the internet. A VTEP, VXLAN tunnel endpoint. This is the, I guess you would call it the ingress and egress point of the host for VXLAN. It is a VM kernel interface that we put onto your ESXi host. Just like you've got your management VM kernel and you've got your vMotion VM kernel, now you're going to have a VTEP, or VXLAN tunnel endpoint. And all this is an encapsulation point. When you're sending a layer 2 packet across the wire over layer 3, you encapsulate it at the VTEP, you send it across, and then you decapsulate it at the other VTEP. We'll go over that a little bit more here in just a bit. So as I've said a couple of times here, this technology for VXLAN, it's a ratified standard. It's IETF. Cisco, Citrix, Red Hat, Brocade, Arista, Dell has also worked on it, and VM worked on it. So it's not like something proprietary that we're doing. Lots of companies do this. There's lots of top-of-rack switch vendors these days that do hardware VTEP. They do that because they have the Broadcom chip in them that allow them to do VXLAN offload. And that's how we work with them to communicate with NSX control plane in order to do the hardware VTEP, which is basically a VLAN to VXLAN bridge at the top of rack. So let's kind of look here. When you create VMs, or you have VMs in an environment, and you create a logical switch, that logical switch is just a layer 2 broadcast domain, just like any other physical switch. If you look on this map here, they're not connected to any routing. So you can ping between the devices, but you can't ping outbound. You can't ping another logical segment. There has to be a routing device in there for layer 3. So if we look at the physical view here, VMs in a single logical segment, we've got transport subnet A, which is 150.0, and transport subnet B, which is 250.0. You can kind of think of these as two different physical locations, and then they've got their physical network underneath. That could be, you know, using any form of maybe an MPLS circuit or dark fiber or something like that. It could be layer 2, it could be layer 3. Really, it doesn't matter at that point. Our logical segment doesn't care. It just knows that it needs to communicate from host to host and that they are still layer 2.
Hey, Tim.
Yes, sir.
Sorry to cut you off, but we do have a question that is probably timely. Joshua Andrews asked, does that mean we can plan on Cisco VTEP supported by NSX?
That's a fantastic question, and we already have Cisco support for hardware VTEP. It is a very, very small amount, but it's a start. And that is specifically the Cisco 9K switch, but not all of them. It is just the a small range of 9300s for the Nexus 9K that supports it. We don't just go out and like buy a bunch of switches and certify them. We work with the switch vendor to say, hey, does it meet criteria ABC? Yes. So okay, send us one and we'll certify it. Cisco, obviously, because of ACI, I would imagine, was a little bit behind on certifying with us. Eventually we got one, I think it was like a 9396 switch, but at this point in time now I believe we have, I think there's like 6 or 8 different 9300 series that are currently certified. If you need that, reach out to me and I can get that list to you. But absolutely they are working with us on this.
Awesome, thank you.
Muted.
So we
Unmuted.
have a visualization of VDS with VXLAN, and I really don't like this drawing because it looks like the VTEP is up in user space up with the VM, and that's not the case at all. VTEP is down in the ESXi host. I would put it near the bottom between the host and IP fabric, because just like your distributed virtual uplinks that go to your management, your vMotion, your vSAN, and all that, that's exactly where you're going to put your uplink for VTEP. This is going to be an IP range that you want set up, and those are where our control plane kind of keeps track of where the VMs exist based on that VTEP address. So when it comes to VTEPs, a single distributed virtual port group is set up for that. Each logical switch is a layer 2 broadcast domain, just like any other physical switch or switch fabric, if you will. As far as that logical switch goes, that's how far the broadcast domain goes. And a logical switch can absolutely span multiple VDSs if you have multiple VDS inside of your transport zone. So if we look here, we're going to kind of look at a traffic flow on a VXLAN backed VDS. And there's one important thing to note. Last week I said that, you know, you may have seen some nomenclature of NSX vSwitch. And all that is the VDS that you have today with the extra VIBs for NSX. And that's exactly the same that you'll see inside of your vSphere web client. So if you're an NSX admin and you start creating all these logical switches, your vSphere admin is going to see all these new port groups. Because as far as VMware is concerned, it's just another port group, except it's a VXLAN-backed port group instead of a VLAN-backed port group. Generally, you can tell the difference because the VXLAN-backed port group from NSX for a logical switch is going to have a long string of information for the name, and then at the end it'll have like WebLS or whatever you happen to name the switch. So if we kind of look here, we've got a layer 2 frame that needs to be sent, and it's going to be sent to the VTEP. At that point in time, it's going to be encapsulated IP UDP, and that could be TCP, it could be UDP, it really doesn't matter. For our purposes, it's encapsulated IP UDP. It's going to be sent across the IP fabric. That could be, again, from rack to rack, from site to site, all the way across the world. We've got videos of one of our soft layer gurus setting up a NSX environment from Dallas to Australia with one giant layer 2 segment. So imagine just as if you were moving a VM in the same rack, moving it all the way across to the other side of the world, not re-IPing, not doing anything like that. It was, a little slow with the round trip time, but it was still really cool to see that. So once it hits the other side of the distributable port or VTEP, it's going to be decapsulated and sent to the VM. Now those VMs have absolutely no idea they've been encapsulated. So let's kind of take a look at the NSX VXLAN enhancements. We can do multiple VTEPs on a host. Most of the time you're really only going to have one, especially if you're working with like 10 gig or 40 gig. But if you are trying to use maybe 1 gig and you're trying to get a little more performance out of it, depending on your needs, you can set up multiple VTEPs and do uplink load balancing. So if you're doing encapsulation, but you have DSCP and COS tags, all of that information is going to be copied to the VXLAN header. So if you're doing quality of service, that quality of service tagging will still be on the outside. So you can still do quality of service even on encapsulated traffic. Now the dedicated TCP IP stack for VXLAN. This is actually kind of a big deal. For the longest time, VMware had one TCP IP stack in ESXi. That's just how it was. You could not have multiple gateways in one host. Then we got layer 3 support for vMotion and things like vSAN. Now we've got multiple TCP IP stacks inside of ESXi. VXLAN is one of those dedicated TCP IP stacks. So it has its own gateway, it's got its own everything, all the way through TCP IP. Now, VXLAN hardware offloading. There's a whole lot of cards these days that support VXLAN offload, and most of them, if not all of them, are all Broadcom chip. And we can do things with that for really high throughput and high performance environments. And we can use things like receive side scaling, large receive offload, and stuff like that, and settings like that, where we can kind of kick the performance through the ceiling and really push the limits. There is a major transportation company out of Fort Worth, Texas that just got NSX, and one of their engineers, probably one of the smartest guys I've ever talked to, pushed NSX to its breaking point on the C7000 HP chassis with their specific network cards. They're doing multi-VTEP, really, really high throughput stuff. And they found that if you enable all of these settings, you can really get a lot out of virtual networking.
Tim?
Yes, sir.
There's not a question, but just my question. Oh my God, can you put that in the blog post somewhere? That sounds cool.
So we actually have some performance documents and stuff like that. One of our PMs for NSX puts on the NSX performance presentations, usually at like VMworld and our internal kickoffs and stuff like that. So I'll look for it and get you the information. I know we have it published somewhere, but doing multi-VTEP with all of these different settings, I mean, it makes a huge, huge difference in performance for if you're just using some crap NIC versus a VXLAN offload NIC, and then actually turning on like receive side scaling, which if you're not sure what that is, that allows you to take NIC processing, and instead of using 1 core of your CPU, you're using 4 cores of your CPU. So generally with our performance numbers from what we found fully loaded, you're looking at like 1% of a regular generation ESXi host. So maybe 1 to 5% of 1 core, and then maybe 4 to 6 gigs of RAM. if you turn on receive-side scaling, you're going to be using 1 to 5% of 4 cores for your network offload, and it can really start to push things through.
Nice, nice. Love it.
So looking at our control plane, this is really what we got from the Nicira acquisition in 2013. A lot of people do think that we just bought Nicira and slapped a label on their product and sent it out as NSX. But for the first versions of NSX, version 6.0, if you were to log into the NSX manager, it still said the VCNS manager. So really, the biggest thing that we got from Nicira in the acquisition was their control plane. That allows us to do all of our cool overlay networking without requiring multicast, so IGMP snooping and stuff on the switches, and then PIM multicast routing on your routing infrastructure. With their control plane, it is highly available, so it allows us to take our 3-pack of controllers, spread them out, and kind of allow for a bit of resiliency so that if you do lose some of your control plane, you don't lose any of your traffic if a VM moves. But don't get me wrong, if you lose your vCenter server, you lose your NSX manager, you lose your 3 controllers, everything keeps working exactly as it was when those things lost. All current state still happens. The only issue may arise if you have a VM that migrates to an ESXi host that never participated in that VXLAN network before. It can't update the VNI information, so it will black hole traffic. But as of version 6.3, I believe it's tech preview right now, and it's going to GA in the next version, we have CDO, which allows us to kind of push all of the state information out so that if you lose your control plane, you can still have updates. So if that's an issue for you and you have you want to try to mitigate that risk in a design, then you can definitely work with that. So suppressing ARP traffic. The biggest amount of broadcast traffic on any data center environment today is ARPs. Well, we've taken and turned ARPs into just unicast flows. We do that with our control plane. So when a VM ARPs out to find the MAC address of another VM, the host intercepts that ARP request, sends a unicast to the controllers, it gets the MAC address, and then it sends the ARP respond back so that you don't have a bunch of ARP floods out on your network. So VXLAN system architecture. If you look here, this kind of looks like one of the pictures that we saw last week, and that's showing a couple of vSphere clusters in the NSX manager. The NSX manager, when it comes to our virtual networking in VXLAN, NSX manager talks to the controllers, and the controllers talk to the hosts. Kind of a puppet mastering the puppet master thing. And those controllers are really there to handle all of the environment. It holds the routing tables, it holds the MAC tables, it holds the VTEP tables, so that when a VM asks, hey, where does this VM exist? The controllers respond back to the host with the VTEP address of the host that holds that MAC address. Cluster prep, the MTU size, we went over this before. You just need 1600, and that has the standard 1500 byte frame with our 50 byte header. Segment ID, this is going to be something that you set up, and this is your range of quote-unquote VLAN IDs, which would normally be like 1 to 4,000 on a regular switch. For us, generally, we start at 5,000 and up, and since you can have 10,000 in NSX, you can set that to 5,000 to 15,000, or just 5,000 to 6,000, since most implementations don't use more than 1,000. But really, it all depends on how you're designing the environment. The transport zone, as we said, it defines the scope of how far logical switches reach. It's not a security boundary. I have to keep repeating that. Just like VLANs aren't really a security boundary, even though companies do VLAN segmentation for security, it's not a security boundary. So neither is a transport zone. Replication modes. So we support 3 different replication modes for our virtual networking, and that's unicast, hybrid mode, and multicast mode. Unicast mode is by far and away the most used because it doesn't require any form of multicast on the underlay. We'll never tell you to go out and enable multicast in your environment if it's not already done. If you do already have it, then we might as well take advantage of it, and that's where hybrid and multicast mode come in. And of course, all modes require that MTU of 1600 or greater. So if we look at unicast mode for replication, we've got one VM that sends a request out, and this is for BUM traffic, broadcast unknown unicast and multicast traffic. So for unicast mode, it's simply going to send a unicast stream to all of the hosts. In hybrid mode, it's actually going to take advantage of IGMP snooping for layer 2 at each local side. And it's going to send out, and it's going to allow the layer 2 for that one side to do IGMP, which is multicast for layer 2. And then what it's going to do is it's going to nominate what's called an MTEP on the other side. And it's going to send a unicast to the MTEP, which is then going to do multicast on the other side. It's hybrid mode because we're using multicast as well as a unicast for the other side. And this is because there's going to be no PIM multicast routing. So if it's going over a layer 3 boundary, it can only use multicast in the L2 segment on each side. So true multicast mode, if you've already got PIM multicast and you've got IGMP snooping and everything set up, then, I mean, by all means, let them do what they do best. And that's just sending multicast on L2, which then sends multicast over layer 3 with PIM over to layer 2 IGMP at the other side.
Tim.
Yes, sir.
Appropriate time. I do have a question here for you.
Alrighty.
Matthew Braga asks, are controllers still required if you are running in full multicast mode?
Yes.
I wonder if he means NSX controllers.
Yes. You absolutely, if you are doing overlay networking or network virtualization with NSX, you absolutely have to have the controllers. The controllers are what hold the VTEP tables and everything like that. So you need to be able to know where those things are. And in order to handle it, we do need controllers to handle the replication mode, even if we are offloading it all to multicast. So to answer your question, yes. And it looks like I'm just killing it on the time here. So I'm going to go ahead and flip over, and we will do routing. Can we see the routing one? Make sure that came up right.
Yes.
Perfect. One sec. All right. So for this, we're going to kind of go over distributed versus centralized routing, distributed logical routing overview, deployment technology or topologies, HA scenarios, and then we'll kind of stop and do a summary and Q&A. So distributed versus centralized routing. NSX does both. So if we look at distributed routing, this is kind of the really awesome thing that NSX does, where we take routing and we spread it out amongst all of the hosts. So we've essentially turned every single one of your ESXi hosts into a router. I've taught a lot of these classes where we've got networking guys. There was one guy in particular that kept reiterating and re-asking the same question over and over again. Where is the gateway? Now, in his world of networking, you can point to the box where the gateway exists. With a distributed logical router, you can't. I mean, you can, but it's everywhere. So when he kept saying, where is the gateway? I said, everywhere. Where is the gateway IP address exist? All of the hosts. Where's the gateway MAC address? All of the hosts. So when you create a distributed logical router and you spread out all of these routing information to all of these different hosts, we're creating a virtual MAC and a virtual IP on each one of those hosts so that no matter where that VM exists, that gateway exists on that host. That's just the one thing that I found that with virtualization people, they've already let go of the fact that with virtualization, anything can be anywhere at any time. With networking people, generally, one box is your gateway. So letting go of that and realizing that every single one of these boxes is now its own gateway, or it's now part of a giant virtual gateway, that's what we're doing with distributed routing. Now there's also NSX Edge, or the Edge Services Gateway, or ESG. This is going to be your ingress and egress point to the virtual environment. It is a VM form factor. It's not distributed. This is centralized. This is going to be the peer, if you're using OSPF or BGP, upstream to your physical infrastructure. That's where this is going to start. You're distributed in the general topology, which we'll show you in a bit. DLR peers upstream to the ESG. ESG peers upstream to your physical infrastructure, or other virtual, depending on what it is. So let's look at centralized routing for east-west communication, and this is hairpinning. We'll do some packet walks here. They're kind of tedious, so bear with me, but this kind of shows you exactly what we're working with. So we've got a VM that's existing on a green logical switch. This is VXLAN 5001. It's got an IP of 172.16.10.10, and it needs to communicate with the VM on red logical switch of 172.16.20.10. Now, these exist on the exact same host, but the scenario that we're using is not distributed routing. Now in NSX, we love to tell you, oh, they're on the same host, so you don't have to hit the wire. Well, in this scenario, we have to hit the wire. So we're going to go out and we're going to send the frame over VXLAN, and we're going to send it over to the green logical switch at the destination VTEP where that Edge Services Gateway is doing the routing. As you can see up there, that Edge Services Gateway has 2 .1s on it. That's the interfaces for each one of those logical switches. So once it gets there, the packet's going to be delivered to the gateway. It's going to be routed to the red VXLAN. Then it's going to have to be hairpinned right back over the wire and delivered to VM2. So if we look at the challenges of routing infrastructure at scale, multi-tenant routing complexity, we've seen a lot of customers that are multi-tenancy, and that's either they're a service provider doing true multi-tenancy. They could be a standard development shop that's doing dev tests, staging, prod, QA, and all that mess within the same environment. It could also be if you've got different environments like PCI and non-PCI, how do you kind of keep those separated? With distributed routing, we kind of offload that from physical devices and we run in kernel of your hypervisors. It is fully featured routing. We can do OSPF and BGP, and I swear there's probably a Cisco person out there that's going to ask if we can use EIGRP. The answer is no. No matter what Cisco says, it's not technically an open protocol because nobody uses it. Maybe, I believe Juniper uses it, but it's not the same implementation. We do not do EIGRP. We do static routing, OSPF, and BGP. If you do EIGRP in your data center, we can absolutely redistribute the routes from OSPF or BGP into EIGRP. It's absolutely possible. Not really a huge deal. We have lots of customers that are going that route.
Tim,
yes, sir.
A question maybe from the slide before. I have Matthew Braga asking, can you bridge a VLAN tagged virtual port group to a VXLAN VNI?
So we absolutely can do bridging in NSX, and in fact that's what the Edge Services Gateway really is good for. That does the VLAN to VXLAN bridging because you're doing an uplink to a VLAN and then you're downstreaming it to the VNI for VXLAN. You can also use the distributed logical router and the control VM for bridging. So it just depends on what your use case is and what your requirements are for that. But yes, we can absolutely bridge a VXLAN backport group to a VLAN backport group.
Perfect, thank you.
So the distributed logical router components in the data plane. So this is on each one of the hosts. Logical interfaces are LIFs. These are the actual little legs that hang off of a distributed logical router that you would say is .1. This is where you're going to create your subnets. Just as if you were to create one on a physical router, when you create a LIF and you give it an IP address of 172.16.20.1, that is now that subnet. So that's what you're going to create, and that's going to be the lifts. There are internal lifts and there are uplink lifts. Internal lifts are going to be what you'll connect to all of your logical switches. Your uplink lift is generally connected to a transport logical switch, which goes upstream to a edge services gateway, and we'll talk about that in a little bit more. You can do up to 1,000 lifts per DLR instance. Now that's not saying that you can have 1,000 total lifts in your environment. You can have 1,000 total lifts per DLR. You can have multiple DLRs in your environment. You can have multiple DLRs on a host at any given time. You can have up to 8 uplinks and 992 internal, and an ARP table is maintained per lift. The virtual MAC address is the MAC of the internal lift, so that's going to be that gateway MAC address that exists everywhere. The PMAC is the MAC address for the DD uplink port group, where the actual physical network connects. So let's talk about the components of distributed logical router a little more on the control plane. Last week we talked about how the controllers and the logical router control VM are not in the data path at all. This is another one of those little puppet mastery things. But the only reason you would need to deploy a logical router control VM is if you're doing dynamic routing or bridging. When you do bridging with a distributed logical router, the host that contains the DLR control VM is going to be the host of the bridge, so that all of that information stays on one host at one time. That data is not traversing through the control VM. That control VM just sets the physical host for the bridge. Now, to deploy the logical router control VM when you're deploying it in NSX, if you're using the UI, it's just one little checkbox. You don't have to go out and deploy some template or do anything like that. You just click the button and it deploys the environment. And that allows you to do that peering upstream with OSPF or BGP.
I've got a question for you.
Alrighty.
Joshua Andrews asks, what network should the logical router control VM HA interface be put on? What does it need to talk to?
I don't appreciate that the guy that kind of helped work on the VCAPs is sitting here schooling me on VCAP questions. Don't think that I didn't know your name, because I know you and I know what you're doing.
This is like Stump the Chump. This is awesome.
Yeah, I know. This is awful. Can you repeat that one more time for me?
Sure. What network? He says this is just a test.
All right, we're putting the mic on him in a second. He's going to start presenting.
Okay, yeah.
See how he likes it.
That's a great question that if you want me to, I'll go and look through my VCIX study guide notes for and get back to you.
No, you're on the spot.
Oh,
So,
I know what he's doing.
So again, the question is, you have 10 seconds to reply. I'm sorry.
No.
Yeah, it's in my study notes, man. I don't know offhand. I'd have to look it up.
Yeah.
No worries. We'll put it out on Twitter. Thank you,
All right.
Josh.
Yeah, thanks, Josh.
I'm glad you're here, man. I really am. All right, let's look at a component interaction for logical routing. Dynamic routing protocols are configured for the logical router instance. You're going to set these up through the NSX manager, and that's whether you're using the GUI, that's whether you're using the API, cloud management platform. No matter what, all of that filters through the NSX manager. That information is then going to be pushed down to the controller clusters in the DLR control VM. So when you're setting up, let's say BGP with NSX, you're going to go in and you're going to set the peer of the upstream router. You're going to set the source as the lift that you're going outbound on, and then there's going to be an IP called a protocol IP address. In a standard setup, when you're just peering one interface to one interface, this isn't necessary, but since we're using a puppet master outside of the data path, it needs its own IP address. This just has to be any IP address that's available inside of that subnet that these two are talking on. And once you give it that IP address, the control VM then uses that IP address as the static peering point for dynamic routing. So once that's been set up, your controller cluster is then going to go through and it's going to push updates to the distributed logical router out to all of the hosts. Your peering is done between your NSX edge and your DLR control VM. And then those route updates are pushed from the control VM to the controller cluster and then out to the hosts. The actual data path, while it does look like it's kind of crazy there over to the right, the actual data path goes from the Edge Services Gateway downstream to the DLR and then back up. So you're not going to have any data actually traverse through that little leg to the right. So a DLR VXLAN LIF, this is just going to basically be your connection between the distributed logical router and your logical switches. Those can span all of the VDS that are in a specific transport zone. If you have your transport zone cut down, then it will only go as far as that transport zone. Okay, so I missed this here. So logical distributed routers perform best with VXLAN LIFs. You can absolutely use a distributed logical router with VLAN back port groups that already exist in your environment. But the distributed logical routers are not optimized to do that. They're optimized to be used with VXLAN logical switches.
Tim, I have another question.
Is it from Josh?
No, this is Ken Albone.
All right,
So Ken sent out a tweet and he's asking, can all of this be done via Power NSX or the old school CLI network guys?
And that's a great question. And not working in a CLI made me feel awesome in my SE onboarding training class when I was sitting in there with 5 CCIEs who were peering OSPF for the first time with a user interface and looking dumbfounded because there was no CLI for that specific function. And I was just like, click, 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 and it's done. It's awesome. You can use APIs and stuff like that to actually do the peering. When it comes to CLI for peering, there is no current CLI ability to do the peering unless that's changed in the 6.3 version that I don't know of yet. So you do need to use the API or the UI for that. When it comes to troubleshooting, you can absolutely go into your central CLI and do show IP BGP neighbors or show IP OSPF neighbors, and it'll show you that neighbor state just like you would on any other router. But when it comes to the actual peering, that needs to be done through the NSX manager via UI or API.
So basically what I'm saying is, if you're familiar with REST APIs like Postman tools or other like that, yes, you can script it, but maybe not everything through Power NSX.
Yes, and Power NSX is actually really new in the grand scheme of things. They are doing fantastic things with it, but it is not anywhere near fully featured as, say, the API is.
Okay.
So it's getting there, but the API, and you can actually script the API with Power CLI. It's just, pushing XML API commands. So you can absolutely use that to script the API call. You could do it with Python or just use Postman. But as of like native commandlets for Power NSX to do that, we're not quite there yet.
Thank you so much.
So looking at a logical network topology here, a DLR VXLAN LIF, this is kind of showing the upstream. We have our VM 172.16.20.10 connected to VXLAN 5001, and that's connected directly to the DLR. The LIF of that DLR has an IP address of 172.16.20.1. So obviously that's going to be the gateway for that subnet. Going upstream, we're using OSPF peering, and VXLAN 5002 is just what we call a transport logical switch. And this is just basically a connection between the Edge Services Gateway and the DLR. You'll need the transit logical switch when setting up that adjacency. And those can have literally whatever IP range you want. In this case, it's 192.168.10.1 and 2. So the fact that it's using OSPF peering here, the distributed logical router control VM has to be deployed somewhere, and most likely in this configuration it would have a protocol IP address of 192.168.10.3, and that's what would actually be doing the peering between the ESG and then passing routes through the control plane to DLR. So let's do a packet walk here of distributed east-west routing on the same host. Now, all of our routing is done on the egress host. So if we're going from host to host, you'll see what happens here. But all of the traffic routing is done at the egress. So we've got VM1, and that wants to talk to VM2. And we'll see that we have a source address of 172.16.10.10, and we're trying to get to 172.16.20.10. So that's going to go ahead and send it down to the distributed logical router. It's going to check the routing table, and it's going to route to VXLAN 5002, and then it's going to deliver to VM2. So if we have east-west routing on different hosts, it's going to be the exact same process. We have VM1 that wants to talk to VM2. So it's going to go ahead and check with the router. It's going to check LIF2 for the ARP table. It's going to find that it's MAC2. That's when it's going to be encapsulated with the VXLAN header. It's going to be sent across the transport network to the destination VTEP, where it's going to be decapsulated and then delivered to VM2. So we got now a packet walk for north-south routing for external networks, and this is ingress traffic, so inbound traffic. So we've got a device on an external network with an IP of 192.168.100.10, and it needs to communicate with the VM on the green logical switch. Sorry, I had to clear my throat there. So when it comes in on the external network to the uplink of the Edge Services Gateway is connected to the transit network of VXLAN 5003. So the Edge Services Gateway is going to route that traffic to the next hop router interface, which is 192.168.10.2, and that's going to be the LIF on the distributed logical router. So the packets are then going to be forwarded to the transit network LIF configured on the logical router. So that little logical switch that we saw that was connected between the ESG and the DLR, it has to hit that hop to go across into the what would be considered the external or uplink interface of the DLR. So after the route's looked up and the packet is encapsulated in VXLAN, it's going to be sent across to the VTEP of where VM1 resides. So again, when we need to figure out, no matter whether it's ingress, egress, or what have you, when a VM sends out the request and says, I need to know where MAC this exists, it's going to reply back with the MAC of the VTEP where it exists so that it can be sent over to that VTEP, where the VTEP is then going to have the router deliver the packet to the VM. The VTEPs are how we do all of our encapsulation communication between hosts. That's why when we have one of our little requirements that says the hosts have to be able to talk to each other, that's just one VTEP has to be able to get to another VTEP, whether it be on the same layer 2 or over layer 3 or what have you. They have to be able to communicate somehow. So then that packet is then decapsulated at the destination host, and it's delivered. So let's look at north-south routing here for external networks for egress. So again, we're routed on egress of the host. So when we know we have to egress, it's going to be routed at the first host. So if we look at the VM there that's on the green logical switch, and it needs to contact outside of your environment. And this could be in a different data center. This could actually be in a different tenant in your environment. All depends on your topology. This doesn't mean that it's going all the way out of your data center. It could just be going out of that specific ESG. So we know the packet has to be delivered to the gateway, and that's 172.16.10.1. That's the gateway that exists for that VXLAN. And it goes ahead and checks out and knows that it needs to get to the gateway of 192.168.10.1. So the routing decision is performed, and that is routed on the way out, and it's sent to 192.168.10.1. and it's encapsulated and sent across. It's then sent to the Edge Services Gateway after being decapsulated, where it's then sent outside of the environment. So deployment topologies. This is just a single DLR routing topology. This is one of the most basic topologies there is. If you're doing one of maybe the famous BCIX NV labs, it might have a lab topology kind of sort of similar to this. And the good thing about this is that it kind of shows everything. So you've got your blue, green, orange layer 2 segments or your logical switches. You can see on the blue web tier there's actually a one-armed load balancer off to the side, so we can do one-armed topologies. We can also do inline topologies depending on how you have your load balancers set up. We can do load balancing. Usually they're going to be all with an Edge Services Gateway, so we can do it directly there at the edge on this topology, or we can set it in line or one-armed on your logical switch. So upstream, those are connected to a distributed logical router, and this can, of course, be across, n number of hosts. You've got your transit network of 5020 up to your NSX edge, and it says routing peering. Again, this can be OSPF or BGP, and that's between your distributed router and your edge, and then upstream to your physical router or whatever your next hop router of choice is going to be. And that you can actually see there that the NSX edge is where we're doing that bridge between VLAN and VXLAN. And it's not doing layer 2 bridging, so to speak, in this specific topology. It's just kind of making that connection between a VLAN backport group and a VXLAN. So multi-tenant DLR routing topology. This is extremely common, whether you're doing true multi-tenancy or even just application lifecycle kind of stuff. Anything where you would want to have multiple separated logical segments. And this, where it says DLR instance 1 and 2, this could also be on the exact same host. It could be spread across multiple hosts, multiple clusters. This is just kind of the logical topology here. And if we notice, we have our DLR instance of 1 and then 9, so you can have a whole bunch of these things depending on your architecture. And all of those are peered upstream to an NSX edge with OSPF, BGP, or static routing. And then you have your NSX edge that's peered upstream. So let's kind of look at the high availability models that we have for our routing here. So we have an active standby HA model, and this just uses exactly what it says, one active, one standby. If one fails, we have dead timers that can go ahead and fail over. There's the standalone HA model that's pictured here, but that's actually been deprecated. We now have active standby, or we also have ECMP, or equal cost multipathing, and we can actually do up to 8 Edge Services Gateways devices in an ECMP model, and that'll aggregate from 10 up to 80 gigs worth of north-south traffic for your environment. And that was actually introduced with NSX 6.1. We are now on 6.3. So it looks like we've got about 5 minutes left, and we've hit the end of the switching and routing segments. Do we have anything else? Questions, comments, concerns?
Everybody left. No, I'm kidding. Dude, this is an awesome presentation. No, I'm serious. I've learned a lot. I know a little, but you packed a lot of information in those slides. People are asking for the slides. I already directed them to actually tweet at you if they want to see how they can get them.
Yes, really.
Honestly, thank you so much, because this has been a very good presentation.
Well, I'm glad to hear it. Glad everybody got some stuff out of it. I'm glad Josh could show up and kind of play stump the jump a little bit, which he won that round. And as far as getting the slides is concerned, ping me on Twitter, and I can do PDF versions of the slides.
Yeah, that was for, what was that for? I forget the person's name. Cool.
Our
All
friend,
right.
Tim O'Hara.
I have 22 notifications in Twitter. Okay.
Don't mind us. We were just having fun on the back end.
Awesome. I can't wait. That'll be fun to catch up on.
Cool. Okay, so no questions live, no questions on the Twitter feed. Let me refresh one more time. I think that we are good. Tim, that was absolutely fantastic. Thank you very much for taking time to do that.
Absolutely. Glad to do it, and I believe we have one more next week, and I can't for the life of me remember what we have. I believe it's distributed firewall, edge services gateway, and maybe something else.
Hold on, I'm pulling it up right now. It is.
Yep. You got a kudos from Dinesh Padmanabhan. I hope I said that right. He said, great session. Thank you, guys.
Yeah, Edge Gateway, DFW, and Basic Design is next week.
Ah, cool. I like my design slides. Those are fun. So we'll go over the distributed firewall, which is a huge thing, and I wish we had an entire thing just for that. But design is also kind of cool because we'll go over the reference architecture a little bit and kind of what we're seeing in customers.
And we will definitely be there. Okay. Thanks everybody for attending, and have a good evening.